Alright, today we're going to answer some questions with a calculator, and it's a review question, so it's going to involve some concepts from all over the place. The question is to draw an XY position graph for a catapult that can apply a force of 320 newtons to a 1.6 kilogram object for 0.7 seconds, and we'll shoot this object out at an angle of 25 degrees and see how far it travels. So, the first thing we might want to do is just look at some momentum ideas and calculate what velocity we could throw this object at. Remember that momentum is delta P is equal to mass times delta V. That's change in momentum is equal to mass times change in velocity. That's also equal to a force times a change in time. And so in this particular problem, we know everything in there except for the change in velocity. So let's simply rewrite this. The change in velocity is equal to the force times the change in time divided by the mass. And so for our object of 320 newtons times 0.7 seconds divided by divided by the mass of 1.6, and if we type that in, that's 320. Actually, I need to get out of this mode a second. Clear. And get out to regular y equals mode. And that's 320 times 0.7 divided by 1.6. So the velocity that we're going to be throwing our objects out is at 140, and this is the metric system, and everything with a metric unit, so that's 140 meters per second. So now we can go to the y equals screen. Before we do that, make sure that you have hit mode, and that you are in parametric mode, and also that you're in degree mode. Parametric is what allows you to do x equals and y equals equations, and degree mode is because we're going to use an angle that's in degrees and not radians. So then press the y equals button. I can get to it here. Maybe I can't get to it. So that's the graph. Let's try this again. I gotta move my magnifying glass. There we go. So we got the y equals button, and we will type in for the x equals equation, we're going to type in our velocity of 140 times the cosine of 20. It's going to be 25 degrees. And then for y equals, oops, I need a t. It's an important fact. So that's not a t. Let's try this again. There we go. And then 140 times the sine. That's not the sine either. Times the sine of 25t. That's for the initial velocity term. And then you've got plus 0.5 times negative 9.8 because of gravity t squared. So, or t times t can work too. So if we just hit graph right now, I don't know what we'll see because I don't have any clue about window settings, what I've got so far. So I'm going to go ahead and press the window button, and right now it's kind of a guessing game as to what window settings I'll use. I'm going to estimate that 10 seconds worth of flight will be enough, and 140 meters per second is pretty fast, and so I wouldn't be surprised if it goes at least 200 or 300 meters. Let's go out to 1,000 a second just to check, and then, oops, I'm going to go to 1,000, and then vertically, maybe 200. It probably won't go very high. And that looks like a possibility. We'll graph and see how things look. So, looks like I wasn't quite far enough, surprisingly. So, we'll go back to Window and just stretch our X max out maybe to 2,000. And we'll go by 200s. And hit graph. And looks like it comes down not quite enough time, so maybe another 4 or 5 seconds on the time, 15 seconds, and graph again. And if we hit trace, and then you can move around, and you can see about when it's at various locations. For instance, it looks like it's going to reach its maximum height about 5 or 6 seconds in. So somewhere around 6 seconds at about 175 feet high, or meters high. And then it comes back down again, and looks like it traveled approximately 1,500 feet, somewhere in there. So those are some answers to good window settings. The last question gets at how does the range that we get vary depending on the significant digits of the variables that I stated. For instance, I said 320 newtons. It's a little ambiguous whether that 0 in 320, does that mean is that it's significant or not? I'm going to assume, I'm going to err on the side of caution and say that that 0 is not actually measured, and that the 2 is the estimated digit, which means that the force that I could apply is really anywhere from 300 to 400, and 320 is the best guess. So let's go to the y equals screen again, and we got 140 by doing 320 times 0.7 divided by 1.6. We're going to set up now a range and see how much the variance from 300 all the way up to 400 really makes. And to do that, the first thing I'd like to do is just replace 140 with the calculation that we got to make that. That's 320, and I'll hit insert. Oops, that's not insert. Back to y equals. Back to the y equals screen, and we'll hit second insert, and 320 times 0.7 divided by 1.6, and we'll do the same thing for y1, and that is 320, and I'll hit insert again, second insert, times 0.7 divided by 1.6, and I'm going to graph it just to convince you that this is still going to give us the same picture. So, the same picture as before, it's just now we don't have the 140 in there. We've got a equation instead. And if we go back to the y equals screen, we're going to set up a range, and to do that you can use the little braces. So again, I'll hit insert, and then we'll go down and find the little braces which are above the parentheses. So second parentheses, and notice up there it's got a little brace. So Now I'm going to insert a few things. I'm going to go from 300, and then I'll put a comma, and then I'll leave 320 in there because I'll want to see that particular one too. But then I'll come over here, and I'll hit second insert again, and I'll put comma, and we'll put the final range of 400, and then we will do the closing brace. So notice I've got a range of from 300 to 400, and I also happen to have one value in the middle of that range, the 320 that's posted. We got to repeat these steps for y equals, and we can do again second insert, second brace, and we'll type in 300 and a comma and 320, and then we'll do again second insert, comma 400, and closing brace, second parenthesis. And now when we hit graph, you'll see three different graphs, one representing the lowest possible value, and one representing the actual value that we had, and then a third trajectory, which happens to be the maximum possible range. So we hit graph, and it'll take it a second for it to graph all three of those. This is the lowest possible values. Now it's coming in and graphing the actual 320 value, and now coming in and graphing the maximum from 400. And so 320 falls kind of in between there, and it looks like from the graph that it's gone anywhere from, let's see, that would be the 1, 2, 3, 4, 5, 6, 7th tick mark in, so that'd be a little under 1400 was a possible, and it looks like it could be past 2000 is the maximum. Now, in reality, it'd be pretty bad to be that far off to say that 320 newtons versus 400. Let's pretend instead that maybe that zero was significant, and that it was really 320 was my best guess, as opposed to maybe 319 versus 321. If we go to our y equals screen, we can adjust our range a little bit. Let's suppose we know it's between 310 and 330, and 320 is kind of our best guess at that. If we do the same thing down here, and hit graph, then you'll see that the range is a lot closer together. This is more realistic. Usually you know things fairly close, but so here it looks like it's from just over 1400 to maybe just over 1500. So that gives you some idea of how accurately we know this answer. So it's not really worth looking for the third or fourth decimal place of how far this thing traveled when we really don't know it that precisely. You could do the same sort of thing for the other numbers, the 70 seconds. Maybe it was 0.69 seconds or 0.71 seconds. How does that affect things? Or the angle. You could put a range in the angle and go from anywhere from 20 to 30 with our best guess at 25. And how does that affect things? But just a little more about significant digits.